Hello, everybody. After this short delay, I'm very happy to host Nir Gov. Nir Gov is the PI in the Weizmann since 2004, focusing on developing theoretical models for various phenomena in biology that involve many interacting units, from the collective migration of cells to collective motions of animals within a group. In addition, his lab is studying the dynamic of cell shapes, cell migration, and general non-equilibrium physics. Today he will talk with us on the geometry of decision-making in individuals and collectives, and hopefully no other problems.
Okay.
Near the stage is yours.
Elad, thank you. So it's a pleasure to be here. It's the first time I think I ever give a seminar in computer science. As you see that it's not my field. I'm a physicist working on biology. But I happen to work in recent years on this issue of decision-making, of collectives of animals, of groups of animals, and recently on single animals, so decision-making in a single brain. And then I wanted to organize a conference about it because I thought that would be a good way for me to go into a new field. And I contacted somebody from Mobileye, who is actually also here, not in the audience, but in your department, Chai, and he suggested that I give a seminar about it. So that's how I ended up giving you a seminar today. So it's not going to be about computing, but I hope that maybe some of the ideas of how single animals and group of animals making decisions while navigating will be interesting for you. Something to think about. So many groups of animals are moving together and they do other things together, like hunting or building their homes. But the minimum activity that they do together successfully is that they move together, from fish to locusts to birds. And of course, the number one priority for these groups is not to split, so to stay cohesive. But they still need to take a decision. There's not usually a single leader. Even in ants, the queen is not a leader. She's buried underground and just laying eggs. So it's decisions which are made by all of the individuals, usually rather democratically, even though there is no voting system. And even in systems when there is some hierarchy among the individuals, usually these large decisions are made collectively, are made by all the single individuals together. So how do they decide where to go, for example? So this is a work that is shown here in this movie, which was done by a collaborator of mine, Ian Cousin, in Africa, where he put GPS on a group of baboons, and they are moving together through the savannah. And you see that now there is seems to be a splitting, and then some want to go to the right, and some want to go to the left, and eventually the decision is to go to the left. They never actually split. To split for them in the savannah is death, too many predators. And they all have similar colors, but there is strong hierarchy in the baboon society. So there's alpha male, alpha female, second in rank, third in rank, etc., etc. But still, these decisions were to go are entirely democratic. If the alpha male was in the small group for some reason, because he thought that this avocado tree is better to go to eat now, but the majority went to the mango tree, he will go with the majority. He doesn't probably think or through evolution that he has better smell or eyesight or brain power than the others. So if the majority of noses and ears and eyes decided that the mango tree is the better one today, he goes with them. When he gets there, he fights with them to get the best fruit, since he's the alpha male, but the decisions where to go are done democratically.
What do the different colors mean?
I guess the different female, male, and some other things. Although they are all adults, there are also younger individuals here, but they didn't have any collars on them because it's less ethical, I guess. And then also there's a decision that you have to make by yourself without others to help you make a decision where to go, and also other things like what to eat, etc. So it started with, the work I'll tell you started with concentrating on groups of animals, and I'll get to a single animal, a single brain in the later part. So that's Ian, who made his career in Princeton, but now he's in Germany, and Itai was a PhD student of mine at the time. So Ian already was thinking about this problem for a long time, and he made some very heroic experiments. I say heroic because he told me that this experiment was so tough he will never try it again. You condition some fish to go to the blue target for food, some of them to go to the yellow target for food, and now you mix them with some fish that are unconditioned, so they are we call them uninformed because they have no information. These are cohesive fish. They want to stay together. Still, many times during this experiment, they split, which of course ruins the experiment from the collective decision point of view. And you can ask what will happen. Will they split, or will they make a decision early on, or will they not make a decision for as long as they can, going on the compromise between the two solutions, and then at some point it becomes useless to continue there because there's nothing there. So you are forced to make a decision. And how is that decision dependent on the number of the individuals and the number of uninformed ones? All of these were questions that Ian was asking. And from the theoretical point of view, the study started with simulations. So Ian was already playing with these simulations and made his whole career working with these simulations with a very simple model. In this model, basically, you have, let's say, informed individuals and uninformed individuals. All the individuals try to maintain the same direction of motion as their nearest neighbors. How do they know which direction others are going? Doesn't matter. You can say by eyesight or by some clever calculation. In reality, fish actually cannot do this calculation. They work by simpler algorithms. But this is the simplest algorithm that they thought of almost 20 years ago, that you're basically averaging the direction of motion of all your nearest neighbors, and you are also attracted to others. Without this attraction, these simulated groups very quickly split, and you don't want that. Even with this attraction, as soon as you go to larger groups in the simulations, they split on the time. It's a nightmare to make a simulation run all the way through without splitting. Now you can, of course, crank up this adhesion interaction between them, but then you get them to form almost like a solid, and that's not really... So it's a problem to fine-tune the parameters. Fish in reality don't work by these algorithms, but it's still a very well-tested algorithm for already 20 years to simulate what realistically happens in some flocks. Yeah.
Isn't there an analytic solution for what would happen here? Do you have to do simulations? Everything is linear, no? It's a linear system?
Well, the interactions are highly nonlinear in space, and the spatial organization of this can be very complicated.
But the velocity at any given time, my velocity is just a linear function of the velocity of my neighbors.
Yes,
right?
this is true. No, not linear, because there's also this attraction which is nonlinear with distance.
What is this attraction? Can you say?
It's São Paulo.
I see.
Okay. But even that depends on the number of your neighbors and who are they, and that changes all the time because they are changing direction, changing position. Yeah, so these are the informed subgroups and the uninformed, and I can show you an example of such simulation which works well in the sense that it is running without splitting, and you see that at least in the simulation there was going along the compromise until at the end this group won, the red group. Although at some point it seemed like it was going to the white, and eventually the red group was winning. So now, as I said, you can run these simulations and you can get a lot of data from that, but you don't really understand what's happening because you don't have a solution for it. You don't have really an analytic solution for it. For example, what kind of data do you get from these simulations? You get that as long as the angle between the two targets is small, the group will go along the compromise direction, which is the middle between the two angles, and there's a critical angle at which the group will split to either going to one direction or the other. So this was a solution that already Ian reported from these simulations, but what are the properties of this transition? It's not clear from just running more and more simulations. There was another interesting observation that he saw in the simulations, that as he increases the number of individuals, the nature of this transition changes from something which is smooth to something which is abrupt, which in the language of physics it's like from second order to first order transition, or just a change of the kind of the bifurcation that happens there. as I said, it was poorly understood. How did I get into this? As Elad said, I was working on problems in biological physics to do with cells, how cells are moving, nothing to do with decisions. Cells, I don't think, make many decisions, or at least they make different decisions. But then I met Ofer Feinerman. Maybe you've heard of him. He's the ants person in Weizmann, and he's doing great things about ants. And we worked on how ants make cooperative transport. So there's many ants together that they lift something that one ant cannot move, which is usually food, and they carry it to the nest. Now, it sounds a simple task to do. For you, let's say your friends tell you, let's bring help me with this big couch to a moving apartment. So some of you take the back of the couch, some of the front, and you can talk to each other. The ants cannot talk to each other. So the only way they can communicate while transporting, other times they do it by chemicals, but while transporting a piece of food, they cannot also communicate by chemicals because they have their antennas against this object that they are holding with their mouth, so they cannot at the same time also smell their way home. They only interact through tactile information, through feeling what the others are pulling. Imagine that you have this couch and I close your eyes and ears and you feel that the couch is moving towards you. So you understand that you're in the front, right? So you have to go back. Or you feel that the couch is being taken away from you. You understand that you're in the back. Either you should push, but probably those in the front won't like it. At least you should lift, right? So that it's off the ground. And that's exactly what the ants are doing. So you can see here that the ants have just two options. They can either try to pull, which is what this ant is trying to do, and then they can also lift. So they have two options, so it's a binary option, whether to lift or to pull. Of course, this is, she doesn't know what to do because there's not enough of them to actually do something. They haven't recruited enough ants to actually lift this object. You could see cars going in the background because this is really done outside. So there's actually, so we made a very simple model for that, which will lead me to the model on groups of animals and the brain. And that model basically says that you have agents. You can think of them as the ants or the individuals in the group. And they can either pull or they can lift. But in the mapping to the groups of animals, there's nothing to lift because the thing that they now carry is the group. So there's nothing to lift off the ground. But there is the notion of either pulling or not pulling. What does it mean to pull? So to pull is to exert some social force on the group that likes to take the group in your direction. It can be in the baboon's case by shouting or other means. It can be in the case of the ants by pulling physically on the objects that others are holding onto it, and that's how they feel the pull. It's a real force. And it can be by other means. So basically, you have two options for each agent. It can be either exerting a force or not exerting a force. And the simplest thing that you can think of is that you have these agents on two opposite sides of this object. For the case of an animal group, the object is the group itself. And they either are informed to go to the target in the top, or they are informed to go to the target in the bottom. So now they have to decide between these two, if it's in one dimension. If it's in two dimensions, like I will show you in a second, then of course there is the notion of this critical angle. We'll get to that. So in terms of a physics model, this is very simple because each of these 0 or 1 is like a single bit or a spin, as we like it, to think about it. And we can write the interaction between them in terms of this Hamiltonian, which basically says that each of these spins has some interaction matrix between them. And the interaction matrix is very simple. Those that are in the same direction are enhancing each other. So they turn, if one is on, it tends to make the others on as well, and inhibitory to the other group. So if one group is winning, the other ones are sort of discouraged from exerting their pull on the group. Okay, that's the simple rule. Yeah.
So here you said the interactions are local.
They're not local. They are all to all. So they feel everybody and they feel everybody. Yeah.
Okay.
Which already simplifies this immensely because there's none of this spatial complication like in the real group. And basically it means in mathematical language that the mean field solution of this Hamiltonian is the exact solution. So there's no problem there. Yeah.
When you say pull, do you mean also push? Or
No, they can either exert this social force on the group to go in their direction, or they can be quiet. Okay?
by lifting? By lifting?
Well, in the case of the ants, it's by lifting. But now, since it's more abstract, it's the carrying of the group itself. There's nothing to lift because there's no real friction now to overcome. So these are in words what I just told you. You can actually solve this Hamiltonian by mean field solution, and you get that there is like a critical temperature above which the system is disordered, and it means that it is in the compromise regime. There's no decision, and there's a low temperature regime where there is a decision, either to go to the top or the bottom. Of course, if everything is symmetric, then the solutions will be symmetric, but you can have some bias towards one solution or the other. I'll get to that in a second. So there's a high temperature disordered phase and a low temperature ordered phase. If you look at the trajectories of this object along one dimension, because as we said, it can be either pulled up or down. So at high temperature, it basically does diffusion. And if you look at the distribution of the instantaneous velocity of this object, it's just a normal distribution around 0. And at low temperature, it is making something which looks like more like a run and tumble, or what we also call persistent random walk. And the distribution of the velocities is double peaked around either all of them being ordered to go up or all of them being ordered to go down. And then the opposite group is, of course, inhibited. Yeah.
You explain what you mean by temperature?
Yeah. So temperature basically. Okay, I should have shown it here. Well, in all of when we write a Hamiltonian in physics, we write the strength of the interaction between the individual agents, in this case the spins, and that interaction has to work against the other contribution at finite temperature in all systems in nature, which is entropy, which tends to disorder the system. So in terms of these spins, as you increase the temperature, it means that they flip from being on to off randomly. So it means basically that the value of this temperature has to be thought of as with respect to the strength of the interaction. Which one is stronger? The interaction, which wants to make them all on here, because they enhance each other, and then if these are all on, these will be all off. That's what the interaction wants, in order to minimize this energy, with a minus sign here. Or temperature, which wants to maximize entropy, which means that they just flip on and off randomly, so that you have the maximum number of states for the system. So thermodynamically, that's the you can think of noise versus order. Okay.
Like if the system is in a given state in a high temperature, then temperature will in the next step it will flip. Exactly. It's how likely you are to flip. Exactly. Irrespective of the interactions. So temperature doesn't care about the interaction. It tends to disorder this system.
There's no interaction with the environment in this case? I mean, there's like a right decision that you can get from sensing the environment?
So the environment is already there in the sense that these ones are pointing towards some target that is there. If there's no target there, then these ones are meaningless in that sense, that they're informed towards something. But if there is nothing there, what should they be informed for? Okay, so in that sense, the environment is already encoded in those spins. Okay, so you can think of a symmetric system like we saw before when they are all the same, but you can also think of a system where there is a small bias. Let's say you can describe this bias by either having an external field on top of the internal interactions, or you can say that simply the number of spins pointing to one direction is slightly larger than the spins pointing in the other direction. So you can introduce the bias either way, it doesn't really matter. You can again do the mean field solutions. What is interesting is, of course, now the nice symmetric transition is gone. You get some finite drift also at high temperature because of this bias. At low temperature, what is actually interesting to note is that at low enough temperature, you still have two solutions, in the sense that the system can actually be metastably locked in the wrong direction. In this case, the bias is towards the top target. That's sort of the correct target, that more baboons think that it's the right place to go to. But still, the system can actually get locked in a metastable state, but it's still locally stable and can be stable for enough time that you get to the wrong direction if the temperature is low enough. So and that again shows you the role of temperature. Who asked me the role of temperature? So you can actually now run simulations of this one-dimensional system, and you can ask, what's the probability of reaching the wrong decision, wrong target, the target of the minimum group, the group that is smaller, not the maximal group. And you can see that indeed at low temperatures, there's a significant probability that you'll get it wrong, that you'll end up in the wrong, in the minority target. Of course, for running such simulation, you have to decide what is actually the length here. So far, we didn't have the length. We just had one target on top, one target on bottom, but it could have been an infinity. Now that we actually have to calculate probabilities, we have to give some length to this, to the location, the relocation of these targets, in order to calculate a real probability. Okay? And you can see that indeed at high temperatures, where you are basically only doing diffusion, there's no chance of making a mistake because you're only diffusing with a small drift always in the correct direction, so you will eventually have almost no mistakes.
So
okay.
once you reach the target, you stop. That's the game?
Yeah, that's the game. You eat, you stop it, exactly. So you find that everything is in fact controlled here by this number, which is called the Peclet number, which is basically the ratio of the time it takes you to reach the target by pure diffusion versus the time it takes you to reach it by the drift, by the bias, by the fact that there is some, one of the targets which is better than the other. And you can, of course, write it in this compact way, and that eventually actually tells you almost everything that you want. It works quite well. This red line is essentially this exponential of minus the Peclet, and you have to employ some other thing in order to get this limit at very low temperature. At absolute zero temperature, you can also calculate this limit, because then what really happens is that everything is controlled by the initial chance direction that you go to, because temperature is so small, there's no flips anymore, so you're bound to just continue forever in the direction that you chose. And that can give you this low temperature limit of your mistakes. And you can see that you can very well understand most of this behavior. So from that point of view, you might say, aha, it actually is worth, if real flocks are working by this simple model of the spins, it's actually worth for them to be at very high temperatures, or internal noise inside the group, or whatever you want to call this equivalent of this temperature, because they won't make many mistakes. But there is a price to pay for being at such high noise, and at least with this simple model. And the price is how long it takes you to get to the target. And you can see that the time it takes you to get to the target actually increases very strongly as you go deeper into this diffusion regime. Because in this diffusion regime, you're basically almost not moving anywhere. So you waste lots and lots of time actually not doing anything. So yes, you're very accurate, but if you also want to get to a food sometime, you might actually waste hours, and another group of baboons would actually get to that food much earlier than you. So there's always an issue here of finding a trade-off between speed and accuracy. Now, speed-accuracy trade-off is not something that is new to you, because you also see it in everyday life. If I tell you, no, give me an answer quickly, you might make more mistakes if it's in an exam or even in real life where you have to decide on something. If I give you a lot more time, maybe you get it better, you get it more accurately. So you can think of this point that actually maybe the groups have to, within this simple model of spins, have to find the golden path between making too many mistakes and wasting too much time. And you can see that that's actually close to this critical temperature. This temperature, which is the critical temperature for the symmetric system, for the system without any bias. Yeah.
This may be a dumb question, but what plays the role of the temperature amongst ants trying to figure out the right way to pull?
Okay, so for ants, this essentially says how strong do they respond to the interaction in the group, which for them was through the sensing of the pulling of the others, versus how much they ignore it. And in the case of the ants, what we found is that there is some value for this parameter, but it doesn't matter from fitting the data that we had, and it's not zero. So in fact, and what is more interesting in the case of the ants, you can read it in those papers, this value was also close to the transition temperature, which for them was also related to the transition size, like I will show you in a second here. Size of the group, because size is sort of the inverse of temperature for these systems. And it's actually good for the ants not to have zero temperature, so not always to do what the group wants them to do, which means that sometimes an ant in the back, or you working with a couch with your friends, are pulling, which sounds stupid. Why should you pull if everybody wants to take the couch there? But for people, everybody knows what the entrance, and so everybody knows what is the correct direction. For the ants, they don't know what is the correct direction. And in fact, those mistakes of going against the group make the group of the ants sit close to this critical temperature, which makes them the most sensitive to information that comes from outside. So actually, it's good for the ants to make mistakes in that language because of those flipping, because of this temperature, in order to change direction towards the nest. But that's a different story. That's another seminar. Yeah.
How here is accuracy defined? Because like
The probability of reaching the minority target.
The majority.
No, that's the errors. So there's lots of errors here. So accuracy is the 1 minus this. Yeah. So it's 1 here. This is perfectly accurate, and this is much less, 0.6. Yeah.
And how is the optimal there defined?
We didn't define it. We just drew this triangle, this rectangle, because one can now say, okay, there is a cost function which gives some weight to errors, some weight to time, and of course then you'll see that there is some minimum or maximum the way we define. We didn't actually try to work to combine these two into some cost function, because we don't know what is the real cost function for animal groups. So, but it's just clear that there is this trade-off, so we just leave it there. You can put it in all kinds of functions. You can just add them or whatever. Yeah.
So at high temperature, this is kind of like biased random walk, what is happening?
Yes, exactly. It is drift diffusion. Yeah.
So how come you never end at the wrong solution? I mean, if the bias is
Yeah. Of course. This is decaying to zero. It's not absolutely zero. Yeah. Of course. Depends on L. Depends on this Peclet number. Yeah. The longer is the distance, the less is the errors. Yeah. Of course, if the L is very small, you might end up by diffusion also in the wrong, of course. Now what happens in 2 dimensions? Basically, we take the same model as is, only we said that now the interaction, so the interaction within each group is the same as before, only enhancing, only what we call ferromagnetic. And between them, it will now just depend on the cosine of this angle, okay? So if the angle is 180 degrees, it's again -1 as before, so inhibitory. And as they come closer in angle, why should they fight each other? If they're all in the same direction, then they are enhancing each other just as they are enhancing their own group, right? So indeed, you can calculate again by mean field this phase diagram of temperature now versus another parameter, which is angle. And you can see, indeed, there is a compromise regime, there's a critical angle. When there is decision, there is a first-order transition, a second-order transition. So you see some of the phenomenology that was discovered for the simulations of the full group. So this was the simulations of this all of these agents moving together, like I showed you in the movie. And this is this spin model, and you see already that this simple spin model can maybe explain what is going on, but here the parameter that was changed was the number of individuals, and here it's temperature that went down. So can temperature and number be the equivalent of each other but inversely related? So the answer is yes. So we run many of these simulations. This was the most time-consuming part of this project, because as I told you, as soon as you increase the number of these uninformed individuals, these simulations tend to break up and you have to start everything all over again. But you could still map a phase diagram which at least superficially looks like the one I showed you from the spin model, where there's a compromise and there's a decision, but now instead of going down in temperature, you're increasing the number of these uninformed individuals. You can plot the trajectories, you can plot the velocity distribution, and you move again from a single peak to a double peak. So everything looks like the same phenomenology of the simple spin model. Yeah, you can go here and see some trajectories. So when you are in the compromise, in the high temperature, you do these highly meandering or diffusing trajectories. Of course, they look much more rounder because, as you saw, the flock moves like an animal somewhat. like this sausage. And if you look at a larger number, so like lower temperature, you make a much straighter trajectory towards your target. So you can actually understand why there is this equivalent between lower temperature and larger number of these uninformed individuals, because they tend to segregate the two subgroups which are informed. And by separating them, you actually achieve something which is similar to lower temperature, because as we said, lower temperature, it's as if the interactions are much more important than the randomness, than the noise. And indeed, by segregating them, you help these ones only enhance each other, because they're trying to just go with this mean direction of their neighbors, and they have only neighbors of their own kind, so they are enhanced even more. They hardly ever find these guys, and these guys are in the back, so they have very few uninformed individuals to affect, to actually tell them, okay, let's go to the other side. From time to time, they try to do that, but they don't affect many individuals because they are segregated in the back. So by increasing this segregation, you actually increase the strength of the interactions between each subgroup, the inhibition and the enhancement, which is equivalent in our model to the low temperature regime. Yeah.
So is it the number or the ratio between the informed and the uninformed?
It's a good point. We didn't study that fully, so I don't know really to answer you.
So
but I think it's
a fixed ratio?
Sorry.
So you had a fixed ratio and you just changed the total number?
We had a fixed number of informed, and we increased the number of uninformed. So we didn't keep the ratio fixed. From the little experience that I remember that we did with that, it doesn't really matter so much. It's more the average number of them, the total number of them, that is important. That can tell you in which regime roughly you can find yourself.
So if I understand correctly, here the interactions are local, right?
Yes, of course.
But in the model, the mean field model, they were not local.
They're all to all. But there's no spatial information there. They're all the group is like a single point in space.
Yeah, but do we still claim there is like a relation between the model and this system?
We want to claim that there is a relation in the way that the two systems behave, but there's not a one-to-one mapping.
Okay, it's not the same mathematical model.
No, completely not. Yeah.
So you said when you increase the uninformed, the number of uninformed, then they tend to break up more.
Yes.
Is that because something is missing in the model, or it also happens in real life?
So in real life, it sometimes happens in small experiments, but again, small experiments are not very telling of what happens in nature. These groups that are social, like these fish and baboons, you saw even for the case of the baboons under natural conditions, which tend to split them quite strongly, that they fight against this splitting and they eventually stay cohesive. So I guess also in nature, even if you split the school of fish, they will eventually merge together after some time, maybe. Splitting is almost it's almost equivalent to dying. So they will do everything they can not to do that. It means that essentially the way you implement it in this simplified model with these constant attractive interactions is not really what they do. They do something different. It's too simplified, yeah. And people know that, yeah. Now you also see that if you run the simulations on the flock as function of this uninformed number of uninformed individuals, you also see the same trade-off that we saw between the errors and the time it takes you to reach a decision. So again, the same kind of accuracy speed trade-off comes as in our spin model with respect to the same control parameter, which is here the size of the group. It might actually naturally have some effect on what is the natural sizes of these flocks in nature, so that they want to be not too large, not too small, to enjoy making not many errors, but also being fast in making the decision. Yeah, so some noise is good, which might actually limit the size of the group. Yeah. So now I hope I have time. How much do I have? 20 minutes. Okay, great. So now let's go to, can this same spin model actually explain to us what a single animal, in this case you see this cricket or locust, is doing, deciding where to go. Now, when I talk now about decision making in a single brain, you probably have heard or seen experiments of this kind, where either an animal or a human is placed in front of a screen and has to decide between two options. Now, this is a very static configuration where the agent and the objects that is having to decide between are not moving. I mean, here there is a motion which he has to decide, but there's no movement between the object and the decisions. Usually they're also binary. So that's almost 99% of the experiments that have been done on decision making. I'm not an expert in neurobiology, so I cannot tell you all the theory that goes into how a real brain is making such decisions. But what we wanted to try to go is to go beyond that and test how do animals make decisions on the move, on the go. Now, that means that we force the animal to decide while it is in motion towards a few targets, 2 or 3 or more, where it wants to go. Okay, so it's a bit more constraining for the animal in the sense that it doesn't have time to think about what is the best decision and then go. Still, some of the trajectories of the animals seem to be indicative that they do what I just said, that they still, although you force them to be on the motion, they had enough time to look at the options that you gave them, made a decision, and from the word go, they just went straight to the options that were presented to them. So you cannot interrogate those animals by asking them, what did you think about it? But anyway, so there's not many experiments that were done before the data that I will show you. We find one of these works with a mouse that is shown 2 targets. One target is clearly better for this mouse. And you see that there are some straight trajectories. There are some trajectories that might indicate this compromise and then getting a decision. I don't know. We don't have this data, but this is the direction which will go. So again, Ian, unlike in the previous work where he was more mentoring us into this field, here he was doing the experiments. So in Constance, in this Max Planck Institute, they actually have a virtual reality system, which is quite amazing. And in this virtual reality system, they can put all kinds of animals, like for example, this tethered fly, and they can present to the fly a virtual reality scene. The fly is flapping its wings. It's not moving anywhere, but it can rotate without almost any friction. So it can think of the direction in which it's going. And if it's going in a certain direction and there's like some object there, this object will grow larger, making this animal think that it's actually reaching this target. Okay? And similarly also with fish, and even also with the locust. Now the locust is of course walking, so it's walking on some, the old mouse wheels. If some of you remember that there was this thing, the mouse with a wheel. So he walks on this, it walks on this wheel, and can again the wheel changes the surrounding in this virtual reality. For the fish, it's much more complicated because the fish is really swimming in a fishbowl. So you have to have a camera that constantly tracks the fish, feeds the location and of the eyes of the fish to a computer, and the computer is changing a projection on the fishbowl, for example, to make the fish think that there is a pillar here, but there is no pillar here. But still, the fish avoids this pillar because he thinks there is a pillar there. Now it means that, of course, you cannot have 2 real fish in the same fishbowl because the scene is organized only for the eyes of a single fish. But you can make that fish think that there's other virtual reality fish that it needs to now follow. Now, of course, these virtual reality fish don't make any motion in the water, but apparently, although these fish do have sensing for water motion, it's enough for them to see something that looks roughly like their own kind, and they will try to follow it, okay? Unless it's moving too fast, for example. So that's like all I can tell you about the experimental side, but it's quite amazing. Now, we said that each agent is like a spin, and it applies some force on the group, and we didn't say how this agent knows where the target is, but we assume that each agent has eyes, has a brain, understands what is the vector towards that direction. So all of these assumptions mean that in the brain there is some representation of vectors in real space. Now, you know about the place cells, and there was some Nobel Prizes about how the brain, your brain, our brains, actually knows where I am and where you are now in this space. And there is a map of that in my brain now. Simpler brains like the fly have something which looks like a ring, and in brain sciences here, some Polinsky and people have been working on ring models of representation of the real space around the brain, inside the brain, for many years. So I will not go into any of these details, but again, we will think of all of these representations still in terms of these simple spins, only that we now assume that they represent inside the brain a direction of a target in space, okay? So again, by now you're used to this representation. The only extra thing that will be different from what I told you before is that the interaction matrix is not going to be necessarily a simple cosine as function of the angle, but can be something different. And in fact, we will go to something which changes from positive to negative at a smaller angle. And in order to represent that in the simplest way we could think of, we actually modified Euclidean space into something non-Euclidean by mapping all the angles by taking the real angle between two targets, let's say, or three targets, to some power, Ni, and then plugging this modified angle into the same cosine function that we had before. And that gives you this type of interaction, which means that you change from enhancing to inhibitory at a smaller angle, depending on the value of this Ni. If Ni is 1, you go back to the simple cosine. If Ni is larger or smaller than 1, well, if it's smaller than 1, then you reduce this angular spread which essentially means that you give larger weight to small changes in angle straight ahead of you. So small changes in between two targets ahead of you, you're enhancing the meaning of that angular difference. You are enhancing what it means for you. While other angles you care less. So you sort of give more focus on what is in front of you by enhancing the effect of these small angular differences. Why do we do that? And why do I say that Ni is 0.5 and not 0.62? Because surprisingly, by fitting the data from all of these animals, from fish, fly, and locust, to the simple spin model, we found that all of them can be fitted really nicely, although the data is quite scattered, as I'll show you, by taking Ni to be 0.5. Now, is it the same for all of them? Can be one 0.45 and the other one 0.55? I don't know. But it means that roughly they're all in this ballpark of number. Certainly not 1. So, and it's significant that it's not 1. I hope I show you even the consequences of that. So it's a spin system on the move. So a single fly has the same, between two targets, has the same phase diagram that we saw before between decision and compromise, which means essentially it moves up to some angle and then it has to split. And if you look at the experimental, this is less interesting. If you look at the simulations, you can actually not only solve the mean field trajectories, you can also run computer simulations and with noise and with a finite number of spins and temperature, so you get some fuzzy heat map after running many simulations. And you can now look at the experimental data, for example, for the fly and the locust. And there is some massaging of the data here, okay? The data is not so clean, but at least there is a nice bifurcation that you see for the case of two targets. Now again, for the case of two targets, you might not be very surprised because, what else can they do? They cannot continue here because there's nothing here. So it mostly could have gone here and then diffuse up to some point. That seems to be very wasteful in terms of length of trajectory. They could have decided from the word go which one they prefer, and I'll show you that actually there are some flies that consistently only do that, but most of the flies did something in between, which means that they did overall trajectories that look like that. So it's at least encouraging, I would say, at this stage, right? But then we looked at what happens when you have three targets. Now that's already something that hardly ever people looked at when they did decision making for people, even in a static situation. They only give binary choices. Now you have 3 targets, a central one and 2 edge ones. And now you have actually very far away, you're moving at a compromise for all 3 targets because all of these angles are too small to require to make a decision. So you continue along the compromise until you reach a critical angle where you give up on one of the edge targets. Okay, so let's say you go up here, you gave up on this one, but between these two, you still are in some compromise. You haven't yet made a decision there. And then, so this one you can actually calculate for mean field. Then the next stage of the bifurcations, you have to actually calculate the trajectory itself. You cannot actually do it from the phase diagram itself. And you can calculate what would be the map of these trajectories. There is some mess going on here. I'll get to that, I guess, in a second. But if you forget about the mess here and you consider that all of the trajectories that reach here are in the central target, then you have a simple bifurcation that we said in the beginning, that you give up on one of the edge targets, but you are still in some compromise between the remaining ones, and then you decide between them. So you basically break up this 3-way choice into a series of binary choices. It's like I tell you, you want sushi, hamburger, or pizza. So I guess you could say I considered all of them constantly until the last second I gave you an answer. But you could say, hamburger is too heavy for me now, so it's between pizza and sushi, and then you make the second decision. So you break it up, okay, into a series of easier decisions or binary decisions. I don't know if that's what you do when I ask you what you want to eat. This is navigation. This is not the same. Everything here comes from real space angles. I don't know what is the representation of something more abstract like food. You know, I hope we'll get to that at some point. Yeah.
I think I did read at some point that's how the brain makes decisions by binary. Binary choice.
And of course, you can think of other examples. I don't know. You have 5 political parties that roughly represent you. Do you really, until the last minute, think of all 5 of them, or you've reduced it already down to 2 at the last minute, or something like that? Okay. Now, what is nice is that for the first time, we had data about animals moving in this field of 3 options, and I think you can roughly see, I would say roughly see, the same hierarchy of decisions. As I told you before, the story is not so clean because there are consistently those individuals that make only direct tracks. So these individuals here with the gray bars, for tens of experiments, they only did the direct tracks. Those here did some mixture of the 2 of them, and those consistently for tens of repetitions only did the bifurcated trajectories. Now, and the same thing also for the locals. Now, you could say that it's therefore indicative that there is some individuality among the animals. They are not identical, which is, of course, clear. And you can actually explain these direct trajectories also in our model if you take this Ni parameter to be slightly smaller. Because the smaller it is, this critical angle is getting smaller, and you can actually say that now you make a bifurcation so close to the beginning that it's equivalent in the experiment to actually going straight. So there is probably this Ni parameter, which I told you it's half, it looks like a magic number. It's probably spread in the population, but it is roughly peaked at 0.5.
Did you say that this variation between if the bifurcation happens is dependent on the species? Are there some species that they have more individuality than other species?
So I showed only flies and locusts, and in both of them you had a mixture of individuals that are purely direct tracks, those that are purely bifurcated tracks, and those in the middle. Just to show you what is the effect of changing Ni from 1 to 0.5. So for 2 targets, it doesn't seem to change very much. It just brings this bifurcation point backwards a little bit. But for 3 targets, it's much more pronounced, because for 3 targets, you see that for Ni equal 1, which is the regular cosine interaction, you make all the bifurcations super close to the line of targets. And in fact, the second bifurcation is almost at the central target. It doesn't look like a very good rule to use if you want to forage equally. What do I mean forage equally? You're an animal presented with 3 equal targets. You're looking for food or for something, mate or shelter. There's nothing to tell you which one is better, at least at this stage. They all look identical. So sensory information is identical. Why would you make trajectories which are so biased towards the central target just because geometrically it's in the center, and not have a rule that will actually make you forage around this field of options much more equally, which is exactly what this Nir Gov 1 is doing. You can even see it from the trajectories. So that already gives you, maybe you and us, maybe some hints why animals prefer to work with this rule and not with the simple cosine rule. Okay, so what happens here in this mess here? So first of all, you can run simulations if you don't believe the mean field solutions for the trajectories, and you will see that also in the simulations there is something strange going on there. And if you zoom in there, you can actually see that it's actually really interesting. It might be a theoretical curiosity, we don't know, but the first bifurcation we said it's very simple to understand. You give up on one of the edge targets. The next one is actually such that indeed you make a second decision possible. Go there or go. No, but you don't actually go there. You go to another direction which is still a compromise between these two. And then you split, again, going straight to the edge target, but the other one is still not taking you to the central target. It takes you again up towards a direction which is still a compromise between these two, and so on and so forth. So it seems like you never actually reach the central target like this, because you're always splitting off directly to the edge targets, but you never actually get to the central target. Of course, this is ideal trajectories, no noise and no finite size of the targets, but it's still cool. It can remind you of this Zeno effect that you are trying to get somewhere, but in smaller and smaller steps that you never get there. You can change the geometry of these targets from being on a circle to being on a line. Everything slightly changes, but this sort of fractal-like bifurcation is still there. When you change the geometry even further, so you take these two targets further to the left, this whole infinite series of bifurcations goes away, and you have some space-filling trajectories. So we're still studying what's all this geometrical richness, and it's a new system to think about, because spin systems have been studied in physics for 100 years for magnetism, but they never were investigated in this out of equilibrium situation. Why do I say it's out of equilibrium? Because usually spins in a magnet, like the magnet on your refrigerator, you don't care which direction they point. As long as they have some direction, all of them are pointing in the same direction. It's a ferromagnet, and it will stick to your refrigerator and not fall under gravity. But here, the direction in which those spins are pointing is constantly changing as you move in space. So it's a constantly changing Hamiltonian, because the direction is affecting the interaction between them. So that's an out of equilibrium system. That's not what thermodynamics solved for us in the last 100 years. Okay, so I jump over this and I get to, okay, so we can make beautiful predictions from the model. What happens if you start here? And this is the field of targets that's presented to you. So there's 6 of them. Add one more, and suddenly the whole shape changes very dramatically. Even 4 is interesting, and 5, you get all kinds of shapes of bifurcations. Is this what they see in experiments? I don't know, because they have stopped at 3. They said, okay, beyond 3 is, even in the virtual reality, is super problematic. These are experimental data for 2 and 3, but again, on simple symmetric cases, they look like the model predicts, but again, it's less impressive because they are not as beautiful as with larger number.
The average of all individuals?
So this is the average of all the individuals that show some bifurcations.
Only the ones that show bifurcations.
Well, in this case, you can also include those that give direct tracks, because they will add to the same behavior. Yeah. So there's another prediction which we think is very interesting. Why would animals actually prefer to be tuned such that they do go through a bifurcation? So here I'll suggest to you one thing, and the suggestion is that when you go through this bifurcation, you're actually going through a phase transition, like in physics phase transition, and that means that at the transition, you are the most sensitive, which means that this object, which is called the susceptibility, how susceptible you are to respond to an external perturbation, is in fact diverging in the thermodynamic limit. In the finite size system, it will just peak, and it means that you're the most sensitive there. That's like the behavior of the ants for responding to information where is the nest. And indeed, if you run simulations, you can run simulations where you go through this high susceptibility region before reaching the targets, or you can start beyond that bifurcation and reach the targets straight, and you can see what's the probability of getting to the correct target, the target which there has a slight bias towards, and the probability of reaching the correct target beyond the critical angle. So these are predictions. They haven't actually managed yet to do experiments with it. They're doing now it on locusts, because apparently it's easy to show these animals on virtual reality some targets like black bars that they view as attractive to some extent. But how do you make one slightly less attractive than the other? Make it fuzzy. How do you know it's less attractive? Maybe it's more attractive. So it's not so easy to know how to do that, but I think they now do experiments on that. And they will actually test if indeed starting beyond the transition or this bifurcation or above, after it, affects the accuracy of reaching the correct target, the target that has a slight, that you have a slight preference for. So this will be tested. Now you can ask also what determines the value of these parameters. There's two parameters in our model. Before we had only one parameter, but now we also have this tuning parameter of how do you modify Euclidean space into something non-Euclidean. And you can already see, at least in the model, what's the difference. If you have two targets and you go with high temperature, you're above the critical temperature, then there's no bifurcation, and you go all the way here, and here you make this very long diffusion until you reach the correct target. It's very accurate, but takes you a super long time to get there. But for three targets, it's even worse if you don't go through bifurcation. Because for three targets at high temperature, you always end up in the central target. And that, again, is not very useful if you want to forage targets that are seemingly identical, to have a rule of navigation which always gets you to the one which is geometrically in the center. Why should that be the one that's best to always check? Now, so I convinced you the temperature should be below the critical temperature, but what's so bad about Ni equal 1? Why not stay with the simple cosine of Euclidean space? So these are the mean field trajectories between four targets. And what you see is that you never reach those central targets, not because of some strange fractal of infinite bifurcations, but you reach this strange infinite loop and you never reach them. So you say, okay, but that's only mean field solution. It's very clean, but in reality there's some noise. So you can actually run this with noise, and you still see that you hardly ever reach them. You reach them with some probability. It's not zero, but it's much lower than the probability of reaching the edge targets, these two. And above the critical temperature, of course, it's the opposite. Above the critical temperature, you always reach the central targets. This is for Ni equal 1. But now, when you do these simulations for Ni equal half, you see that you reach the central targets very well. And in fact, below the critical temperature, it's shifted because it depends here on the number of spin groups. You reach all four targets equally, which is what we think is a good rule for the animal when it wants to forage. So between Ni equal 1, when you almost don't reach the central targets, almost, I mean, depends on the noise, but the underlying trajectories don't want to get you there, to something which is super equal between all of them, it seems very convincing that this lower value of Ni is very useful for making good navigation and foraging between targets that are equally good. Okay, you have a drone that you send out to some mission, and you want that drone to decide where to go. It finds some targets. Why work with this rule? Much better to work with this rule. It will check out all these four targets equally, which is good for you. If in only one of those targets somebody is hiding or something is worth finding there. If you remember the simulations of the flocks of Ian from many years ago, if you run those simulations, again, not only between two targets like Ian did long time ago, but also between three targets, you see again this same hierarchy of bifurcations, which by now you're not surprised, because I convinced you in the first half of the talk that the spin model captures also what happens for the flock model. Although, as I said, there's no one-to-one mapping between the spin model and the flock model. It seems to capture the same phenomenology. It's decision-making during navigation. It's a simple spin model that seems to capture it, although, to be honest, there's many more tests that we need to put it through. It seems to be universal across taxa between animal groups, which I think is quite amazing, I would say, although it managed to really enrage some biologists when we said that, because they like the differences between taxa, and physicists like to make general statements. We think that maybe the reason that it's universal is because all of these individuals have to optimize foraging for food and being also sensitive to small differences between targets. And these constraints, when mapped to such a simple spin model, give you, a very limited range of parameters which satisfy these behaviors. So how the brains of the fish and the locust do this computation is probably different. The wiring of the neurons is different, but at the end of the day, they implement the same algorithm. And I don't know how they do it in the neuron level. For example, there was this recent work by Gabi Maimon, sounds Israeli, I think, in the United States, where they really now think that they are beginning to see how does the brain of the fly really represents vectors in space and can really do vector multiplication, which is similar to this cosine interaction, which is a dot product between two vectors in the brain, but how the neurons actually implement that, right? I mean, it's easy to do it in a computer, but not how the neurons actually implement it. I showed you fish, but I didn't tell you how the fish actually does this. These are the two virtual fish. This is a real experiment, and this is the real fish. The virtual fish have to make a U-turn at some point, because otherwise they just swim out of the fish bowl into the distance, and the real fish will get stuck on the glass. So they have to go back and forth, which means that from time to time the real fish also has to make a U-turn. Here it's somehow having trouble doing that, so he lost them, but he will pick them up on the next round. So this is a slightly more complicated than what I showed you before, because now you're not actually reaching a target, you're chasing a moving target. So it's more difficult because there's also, it's a question of where are you with respect to these moving targets, right? So the simplest thing that we did in the paper that is already published is to think of the motion. So these are the two virtual fish here in red. You can hardly see them, and that's the cumulative distribution of the real fish behind them. To forget about this position, take only the position of the maximum, so that at each choice of distance between the two virtual fish, we just take the real fish to be in a single line behind them, and only along that line we say how does it move. So we reduce it again to a one-dimensional problem. If we do that both for the data and for the modeling, we actually get very nice, I think, agreement between what happens between the model and the experiment. So what we change here on the x-axis is the distance between these two, and as the distance is small, the real fish is in the middle between them as a compromise, but at some point when they move too much apart, it cannot follow a void. It needs to follow either one of them, and that's what happens here. And in the case of three virtual fish, you see a more complicated bifurcations. That's the model, and this is the experiment. So I think that the comparison is at least plausible, but again, what we've done here is a reduction of the problem to one dimension in order to still be able to do it. But in reality, as you saw, it is more complicated. And this is a virtual fish, and this is a real fish simulated now by a new work that we have not published yet, where we are implementing the same spin model, but also allowing for chasing. So also allowing for moving faster or slower as you are chasing some moving target. So that's a work of a master's student of mine that just finished, and we're trying to write it. And you can see, for example, here, when you have two targets, so these are the virtual fish, and this is the real fish, but simulated in our model, you can see that when it's in the compromise, the two neuron groups are both lit up, and at some point, when it makes a decision to go behind one of them, then one spin group goes down, and the other one stays turned on. And this is the cumulative distribution of this of this real fish behind the two virtual fish over many repetitions. by the way, this jerky motion of the virtual fish is to emulate how the real fish is actually moving. They do a burst and glide, so they kick with the tail, and then they glide until they almost stop down, and then they kick again. So this was taken from to make it more realistic. And you can do it even for 3 fish. And again, you can run these simulations, and you can see that the model works rather well. So this is sort of a final slide, and this is a thank you. Yeah, thanks. So the last piece of work was done by Lital, who just finished the master for this chasing fish. Yeah.
Any questions? So so you did not assume that if you are already close to one target, also the weight of like the neuron become more confident?
Good question. No, so far it's still democratic, even if you're coming very close to one target, and there are other targets in your field of view. We assume all of them to be equal. What we are now thinking about implementing is, which we have done also in the case of the ants, is what happens when you get to a target and you find there's nothing there. So yes, you can still see the target, but in some sense it's lost its appeal. So in the case of the ants, we did it by having entry points where ants could come through, but the object that they're carrying could not go through. So as soon as they reach there, they hit an object. Now, hitting that object gives you an opposite force that perfectly cancels the force of the pulling ends. So in one instant, all of this positive feedback in that direction disappears, and new feedbacks in other directions can actually light up. So in the language of what happens in the brain of this animal, what we need to do is to have some external field that will sort of balance and shut off and sort of discourage the attempt of the animal to go in a direction where it finds that there's nothing there or it cannot continue in that direction. And that by shutting off that spin group, that will allow the neuron groups that are representing other targets to be enhanced and get that animal out of being forever stuck trying to get to a target which it cannot or already found that there's nothing there. So we will actually do this discouragement. Now, what you are saying is that actually coming close to a target will raise its weight. You can, of course, implement that easily. So in the case of the chasing of the fish, what we have done is that there is a dependence on the distance, depending on the distance to the target actually tells you how hard you're trying to chase them. But we didn't actually implement that there's a more appeal for a closer target. No, we didn't do that. And it seems to work without it. I don't know what it means, but it's easy to implement that if we want, but we haven't done that yet, and it seems to work.
Thank you.
So thank you again, Nir, for this great talk.
Thank you.